everyone. Welcome to Timberwolf Tutoring. My name is Shiva.
I'm Aiden. And I'm Robin. And today we'll be covering a calculus topic from Unit 3, concavity, extrema, and the mean value theorem. Thank you for watching our video.
In this video, we will cover Rolle's theorem. We will first conceptually cover both Rolle's and a bit of mean value theorem. Next, we will move on to 3 problems, and the third one will be applying Rolle's theorem to the real world.
Hello, so we're going to start with 3.2, which is Rolle's theorem and the mean value theorem today. We're doing it a bit out of order, but I think that will help understand it a bit better. So to start with, let's look at Rolle's theorem, and we have this parabola here. It's restricted to this interval 0 to 8. You can restrict to any interval you want. I just picked this interval arbitrarily. And what Rolle's theorem will say is basically, if your function is both continuous and differentiable on your interval, which it is, and both the starting and ending y values, the output of the function, are the same, so in this case they're both negative 6, then at some point on this function, the slope will be equal to 0, or in other words, the derivative at that point will be equal to 0. So, reasoning for this is, your curve will either start increasing, decreasing, or staying the same. If it's staying the same, then the derivative is 0, we're done. If it's increasing or decreasing, then we know that it will have to change direction at some point to get back to the original y value. Like here, it changes direction right here at 4. And after that, this will be one of your extrema. And because the function is differentiable, the extrema will have to have a derivative of 0 at the point where it changes from increasing to decreasing. And so we can see that by looking at the tangent line. So this tangent line is at x equals 0, and as it travels along the graph, as x increases, you can see the tangent line slope is decreasing and decreasing, and then right at that point where it changes from a positive slope to a negative slope, it will have a slope of 0, which is our solution to Rolle's theorem. So next up we have the mean value theorem, and that's an extension of Rolle's theorem. So what it says is, if you go back to your continuous differentiable function interval, but this time your y values can be different, so in this case the starting one is negative 8 and the ending one is 0, and you draw the line connecting them and take the slope of that line, so in this case the slope of this line here is 1, then, at least at one point on this curve, then the slope of that line will be equal to the slope of this line, or the derivative at that point. So going back to our original function, we can see that Rolle's theorem is basically the mean value theorem here, because the slope between our starting and ending points is just 0, because there's no change in y. So that means that we just have to find a line with slope 0 or derivative 0 on this curve, which is exactly what Rolle's theorem says. So Rolle's theorem is just a special case of the mean value theorem. So now, for this function again, we're going to graph the tangent line. So here's the tangent line at x equals 0. And again, as the tangent line travels along, you can see the x values up here. You can see the slope gets closer and closer to the slope of this line, until right here at about x equals 4, I believe, they become equal. And again, we know this makes sense because this function will either start at a slope greater than, less than, or equal to this tangent line. If it's the same as that, then we're done, obviously. If it's greater than it, then the function will be above this line, as it is here. And to go back to being on the line at the ending point, the slope will have to decrease to be less than the slope of this line. And when it decreases, it will have to go through the slope of this line, so we're done. And same with decreasing, it'll have to increase and go through the slope of this line again. So I hope that helped you understand 3.2 Rolle's theorem, mean value theorem a bit better. And now let's go on to some problems. Alright, so now that we've looked at the conceptual stuff for Rolle's theorem, let's do some practice problems. And let's jump right into them. So first, a quick disclaimer. And the disclaimer is that none of these problems will be the type of problem you'll see on the test. This is just to help you understand a bit better what Rolle's theorem problems actually look like in the real world. So jumping into it, problem 1, we have, is there a point on the function f of x equals x to the 4th minus x cubed minus 9x squared plus 7x plus 14 on the interval -1 to 2, and this is in a closed interval, where f prime of x, or the derivative of x, equals 0. So what this is saying is, you take this complicated function, and you want to find if there's a point on the function on this closed interval where the derivative is equal to 0. And to find this, we know that to find derivative being equal to 0 on an interval, we can use Rolle's theorem. And so the conditions for Rolle's theorem are 1 is continuous, which we know is true because it's a polynomial function. 2 is differentiable, which we know is true because, again, it's a polynomial function. And finally, we need to prove that the starting and ending values of the interval have the same output when you plug them into the function. So we can start with -1, the start value, and we plug that into the function. You can evaluate this on your own if you want. Pause the video if you want to do that. And it turns out when you plug it in, you will get that f of -1 is equal to 0. So now let's try the end value. F of 2, plug it into the function again. Again, feel free to pause the video if you want to solve this yourself. Right, and now that you've had your time to solve it, I'll give away the answer. The answer is that f of 2 is equal to 0. And so we know now that these two values are, in fact, equal. So we met all the conditions for Rolle's theorem, so we can use it now. And what it says is that there will definitely be a point in this interval where the derivative is equal to 0. So that just means we're done. Rolle's theorem holds, so this point exists. And it says QED, which means we solved it. We proved it.
All right, moving on to the second problem. And this example is similar to the last one. So if you'd like, you can pause the video here and try to solve the entire problem by yourself. Let's get started. Is there a point on f of x is equal to x to the 4th plus 2x cubed minus 8x squared minus 10x plus 15 on the interval? And this is a closed interval because of the brackets, -3 to 1, where f prime of x, also known as the derivative of x, is equal to 0. And because the problem is asking us if there's a point on this interval where the derivative is equal to 0, we can use Rolle's theorem. And to prove that the point exists, we need to meet the three conditions of Rolle's theorem. First, we need to prove that the function is continuous on the interval. And once again, it is a polynomial function, so it is continuous on the interval. Next, we need to prove that it is differentiable on the interval, and it is a polynomial function, so it is differentiable on the interval. Finally, there's one last condition that needs to be met, and that is that the outputs of the starting and ending values on the interval are the same. So let's check if that's true. We plug in -3, which is the starting value, into the function, and we get 0. And then we plug in the ending value on the interval, which is 1, into the function, and that is equal to 0. So both the starting and ending values on the interval are equal, and the third condition of Rolle's theorem is met. So now we've proved that there is a point on the interval where the derivative is equal to 0. And that's all you need to do for this problem.
Alright, so finally we have problem 3, and this is a word problem. It's loosely based on problem 11 from one of the homeworks, but it's not entirely the same, so they won't have the same answer. It says, the order and transportation cost C of bottles of Pepsi is approximated by the function C of x equals 1 over x plus x over x plus 3, where x is the order size of bottles of Pepsi in hundreds, and C is the cost in tens of thousands of dollars. So based on this, is there a critical point on the interval 3, 6? And this is a closed interval. In other words, is there a point on this interval where the rate of change of the function C is either equal to 0 or does not exist? Definition of a critical point. So now, because it's a Rolle's theorem video, you've probably already guessed that we're just going to look at the derivative being equal to 0, because that's what Rolle's theorem deals with. So we can ignore the does not exist case, because we only need one of the two. If we're proving it exists, we only need one and not both. So we're setting derivative equal to 0, and to find if there's a point where derivative equals 0, that's what Rolle's theorem says. So we just have to figure out if we can apply Rolle's theorem to this. So first, is the function continuous? And it turns out yes, it is, because the only discontinuities on here are at x equals 0, where the first fraction doesn't exist, and x equals -3, where the second fraction doesn't exist, but neither of these are on 3, 6. Next up, is it differentiable? And yes, it is, because in addition to being continuous, it does not have any vertical tangents or sharp points. And finally, we have to check if the starting and ending values of the interval are the same. So let's go ahead and check that. So first we plug in 3. And this math should be easy enough for you to do in your head. So I'm going to give you 5 seconds. Right, and pause the video if you need more time. And it turns out the answer is f of 3 is 5, 6. So now let's check f of 6. And go ahead and do this one in your head. I'll give you 5 seconds. Pause the video if you need more time. Alright, so now that you've done that, the answer is f of 6 equals 5, 6. So yes, in fact they are equal. So because these 3 conditions hold, we can use Rolle's theorem, and there is a point where the derivative equals 0 on this interval, which means there is in fact a critical point on this interval. QED, we solved it. Right, so I hope this gave you a better understanding of how Rolle's theorem works. If you want to figure out exactly where the critical point is, you can watch our Extrema video for more information. And I hope this helped you, and peace out! Thank you so much for watching our video. If you want to contact us, you can reach out to us on email at timberwolftutoring@gmail.com or on Instagram at timberwolftutoring. Let us know if you have any questions about the topic covered in this video, or if you want to see a specific topic covered on this channel, preferably a math-related topic. And thank you so much for watching our video, it means a lot to us. See you around. This is Robin, signing off.